paper too.
Okay.
Yeah, but the thing is, I'm taking lots of time to complete the paper, or else I'm not able to
Anyone
finish.
is there with you to help you out?
No, ma'am.
There is no one.
Yes, ma'am. Even if they are available, they are only available on Saturday or Sunday. So, but I
Mhm.
can like time myself, ma'am. Maybe I need to like
Practice more.
put- yes, ma'am.
And at the same time, if somebody is sitting with you to guide, so it will save your time actually,
Yes, ma'am.
isn't it?
Yes, ma'am.
So that need to be sorted first.
Yes, ma'am.
Okay. So can you see the page now?
Yes, ma'am.
Okay. So I'm starting with damped harmonic motion. So what I was saying is, suppose here is a fixed time. Okay, and one thing more, Akshita, yesterday you also got late. This is what Miss Sonia had told me because I waited for you like for 10 minutes. More than that, I guess. But you didn't appear, then I left the class. So whenever it happens like that, you are getting late due to another class.
No, ma'am. I thought it will be at 5:30. Like I got confused with today's timing. So I kind of like had another class. So and then I saw the message. So I asked mom if I can join, but she said you had another class. So I
Yeah. Then I could not be able to give you full time, 1 hour time.
yes,
So
ma'am.
that's why, and if any day it is getting happened, no issue, Akshita. I'm completely, I can understand. So you just inform Miss Sonia prior that, ma'am, it could happen or like that. Okay.
Okay, ma'am.
Yeah. So suppose here is a fixed end and here I am having a wave which is traveling throughout the journey like this. So this will be known as undamped wave. Okay. Here the energy is set to be conserved. So the momentum will also be conserved. Okay. So similarly, if I take your damped wave, so the damped wave behaves something like this, that it gets easily damped with the passage of the time. Damp.
Yes, ma'am.
Yeah. So like your sound waves, if you are talking to someone, then after some period of time, the wave energy may get vanished due to air resistance and all the factors. Done. And due to that, the wave gets damped up. Okay. Now, where are they helpful? They are so much helpful if you are aware. Okay. Like if I give you one example. Wait. Let me show you these things.
Yes, ma'am.
Uh, check this picture that I'm sharing with you. Okay. See this. It's a car suspensor. Am I correct?
Yes, ma'am.
Yeah. These are damped wave, undamped wave. Okay. They easily get damped. Sorry. It's a damped wave. Okay. They easily get damped because these suspensors suddenly get stopped. Like just one jerk came and suddenly it gets stopped.
Yes,
Okay.
ma'am.
So this is known as critical damping or heavy damping, I should say. It's a heavy damping. Damp.
Yes, ma'am.
Heavily damped means just after one wave or two wave of the jerk, it will be again a linear line. Done? Okay.
Yes, ma'am.
Now, let's come to the point. So here the major pointer is that suppose when we are dealing with the oscillations, we only consider that the simple harmonic motion is happening. Okay. That is the motion where the acceleration of the body is proportional to the displacement, obviously. Right? From where? From a fixed point. Correct or not? The
Yes, ma'am.
displacement from a fixed point it is happening. Done. Now it is always directed towards the point. Suppose I have a mass on the end of the stiff spring, which is attached to the side of the spaceship. Okay. Like here, I'm having a mass, let's say M, and it is giving X motion here, X motion here. Correct? Done? So it is moving left and right like that. It gets stretched, it gets compressed due to Hooke's law. Okay. And as it is force is proportional to the extension, then obviously we will say that the motion of this particular spring is nothing but minus of kx. Correct?
Yes,
Motion
ma'am.
of this spring is equal to minus of kx. Okay. So basically, what does this imply? This implies that the displacement, what is the displacement? X is the displacement, is nothing but my a cos omega t. Correct or not?
Yes, ma'am.
That means the displacement here, the displacement only playing the role of sinusoidal wave. Correct or not?
Yes, ma'am.
Whose angular frequency is given by 2 pi f, which will be nothing but its natural frequency with which it is waving. Correct?
Yes, ma'am.
Okay. Any doubts still here?
No, ma'am.
Okay. Now, suppose if we add a fluid around the ball, that is this one. Okay. Suppose I add a fluid around it, then it will experience a viscous force, isn't it?
Yes, ma'am.
Okay. Now that viscous force will oppose its motion. So when this force is proportional to the velocity of this mass, so the equation will be something like this. Your F will be equal to ma will be equal to minus kx will be equal to, I can say, minus of some constant term, let's say k, and your velocity. Okay. Why I'm writing this is just a very simple factor. No need to go in a very depth of this. I'm saying how much force you are applying, that much of the acceleration you will observe in the spring system, that is minus kx, and that much of velocity you will observe in the motion of the spring. Correct or not?
Yes, ma'am.
Okay. Now don't go in a very depth part of it. Okay. Now here one thing need to be noted, that if suppose the value of this particular thing, that is the constant term, okay, is actually equivalent to the constant decay, isn't it? It is getting decayed, no? Check in damp. Okay.
Yes,
So it is actually equivalent to the constant decay, and that we can also compare with like the nuclear decays. Okay. That is, if
yes,
it is large, then the amplitude will decrease in a very short time, isn't it? That
yes, ma'am.
basically what I want to convey you, that F is directly proportional to, not directly proportional, but equal to minus kx. So if I want to decrease my displacement, I can increase my minus k value, isn't it?
Yes, ma'am.
Okay. Now that will be very much proportional to your drag force and the velocity. If I
Yes,
increase my drag force with the velocity, okay, let's say my drag force is nothing but bv. B again a constant, and v is the velocity with which it is traveling.
yes, ma'am.
Okay. So if I increase my drag force, that particular thing will also increase my k constant value of my spring. That means if I am filling a oil over here, this will provide a viscous drag to this mass, and hence the x value will get decreased and k value we can increase, isn't it?
Yes, ma'am.
Okay, and if the fluid is viscous in nature, then the damping could be so heavy that the spring would not oscillate at all. And
Yes,
this
ma'am.
is what we use in the suspensors. In the suspensors, inside of this, oil is filled to give the viscous drag, isn't it?
Yes,
Okay.
ma'am.
And it could give the spring not to oscillate at all. And this particular damping now is known as the critical damping. Understood?
Yes, ma'am.
So suddenly the mass will come to its equilibrium position as soon the car gets into the jerk of road jumpers. Okay.
Yes, ma'am.
Okay. Now after this, if the mass suppose returns to its equilibrium position as quickly as possible but without crossing it, okay, that is, If over damping of the system is happening, this will tend to the equilibrium position slowly in comparison to your critical damping. Let me show you the graph, then you will understand it more clearly, I guess. So somewhere like if it's happening, if your fluid is not that much viscous in nature, if a fluid is not viscous in nature, then it will undergo over damping. Understood? And if it is highly viscous in nature, it will undergo critical damping. Understood or not?
Yes, ma'am.
Okay. Now, we are also having some forced vibrations. Let's try to understand those factors also. What are forced vibrations? So basically, when an oscillating system such as mass spring system is disturbed, it will oscillate at its natural frequency, which is given by 1 over 2 pi under root k over m, isn't it?
Yes, ma'am.
Okay, this is not t, but this is f, natural frequency it is. Okay, t is 2 pi under root m over k. Okay, so this is frequency with which it oscillates, and the mass can also be made to vibrate at the frequencies by applying the sinusoidal varying force over it. Done. So
Yes.
here the energy is being transferred from where? From the motor. Okay.
Yes, ma'am.
Okay, let me show you how does it work. Uh, these are nothing but the application question answers. It will come in exam in the form of application. Don't worry. Reasoning question answers majorly.
Yes, ma'am.
Okay. So now check forced vibration and why do we create it? Here I have a system. If I forcefully create the vibration, this particular wheel will rotate on the axle. Correct?
Yes, ma'am.
Okay. So in this case, we require it as per our convenience so that it will derive the wheel. Done? Any doubts over here?
No, ma'am.
Okay, great. Now let's come to the next topic, and that is resonance. Let's have a look now. What do we understand by resonance basically? So in resonance, what happens is, suppose here I have a table and I tap it. Here I had put a sheet of paper over it. Okay. This is a paper sheet. And here I am having iron fillings. Due to my tap, the paper will also vibrate with the same frequency, and the magnetic iron fillings will get aligned in one pattern. Isn't it?
Yes, ma'am.
Okay, so with the help of one object, the other object also undergoes vibration. This particular phenomena is known as resonance.
Yes, ma'am.
Okay, so the definition would be resonance is okay. This
Yes.
phenomena is known as resonance. That is, the amplitude of the resultant wave increases when the driving frequency. What is the driving frequency? This one. I am driving. Okay.
Yes,
Is
ma'am.
equal to the natural frequency of spring mass. Now, I had given you here some other example, that is this one. So this frequency, driving frequency matches with the natural frequency of the paper and hence it get aligned. Okay. So here the amplitude will get doubled up and let me show you that how does it work. So they had given a spring mass system. Spring mass system, I can say, is shown over here. See, this is spring mass system. Okay. So if you
Yes.
are vibrating it with frequency F, that it is going up and down, up and down. So it will create a sinusoidal wave and which will give the double of the amplitude when the driving frequency will match the natural frequency of this particular mass spring system. Done?
Yes, ma'am.
Okay. Now what happens due to damping? Then the effect of damping is something like this. Check. If lighter damping is happening, then it will lose the energy slowly. But if heavy damping is happening, then the amplitude versus frequency graph it is, the amplitude will get to zero at one instance only. Done.
Yes, ma'am.
Where do we see all these things? So let me give you some examples also. So you must have seen the wind chimes. Okay, in wind chimes, you must have seen with the blow of the wind, the chimes also start vibrating. Done? Then after that, you must have seen that the vehicle in which you sit,
Yes, ma'am.
right? There
Yes.
also you will see the resonance factor happening. Let me give you other parts also of this particular thing. So there are some examples and other example, it could be earthquake also, right? As
Yes.
the earth is vibrating, or ultimately automatically you will see that the person standing on earth starts vibrating. Okay. So a truck driver drives past a room and makes the plate rattle on a shelf. Okay. Then opera singer shatters the wine glass. Then infrared radiation resonates the CO2 molecule. Air in the tube resonates to produce the sound. Resonating quartz crystal is basis on the many clocks. Then
Yes.
engine part may break if it resonates with the frequency of the engine. Okay. Tall building can collapse due to natural frequency is same as the frequency of earthquake. Right?
Yes, ma'am.
Okay. Any doubts in the resonance topic?
No, ma'am.
Okay. So this chapter is almost over. We are having just electrical resonance. So already I had explained you the two types of resonance. First is the spring mass system. Then other one, this was here. Where did I show you? Yeah, spring mass system and then the suspensors, etc. I had shown you. Okay. Then I had also given you the resonance examples. Please, electrical resonance do at your own. Done? It's a
Okay,
very
ma'am.
small topic. Same it is. Don't worry. It is same. Okay. You just have to
Yes.
compare it. It's not hard. Okay. A very small topic of the last is remaining. Now, after this,
Yes.
I'm starting with C5 chapter.
Okay, ma'am.
Uh-oh. Where is my page gone? Did I close it?
Yes, ma'am.
Yeah. I have thought, where did it gone? So I'm starting with the C5 chapter now.
Yes, ma'am.
Okay. Check here. C5, and that is your Doppler effect. Okay. Now have a look. What is Doppler effect? So Doppler had basically explained a very simple topic that if suppose here is the source standing and here I am having the receiver. Let's talk about sound wave right now. So when the source is rest, it's creating a wave. The same wavelength and frequency will reach the receiver and it will receive the same wavelength. So it will say that the source is somewhere here. Let's go and go listen the music. Okay. So this is
Yes.
all about rest position. Now, let's take another example. Say my source is moving, say an ambulance on the road, and a person is standing here. Okay, so as soon it comes towards, then it goes away. So this is a part where it is going away. Here it is coming towards. Done. So two situations we are having. So when it is
Yes.
the source and it is traveling continuously, what will happen? These waves exactly get shrink.
Yes, ma'am.
Okay. So the frequency becomes high.
Yes.
And when it goes away, these waves, not to be shown like this now, becomes like this. It goes away. So the wavelength goes on increasing. Why? Because if I fulfill this wave, it will be somewhere like this. Understood?
Yes, ma'am.
Understood? So when it is
Yes.
coming towards, you will see this particular thing. Okay, let me show you this thing. Hmm.
And then if the frequency, like if the wave is, if the sound is like going away from the person, then the frequency will be less.
Yeah, exactly. Exactly. Okay. So we call it observed frequency and the received frequency. Done. Now, in your syllabus, we are having two examples for this. That what happens if the source is moving away? What happens if the receiver is going away? So here is it. Check. So the observed frequency for sound waves and mechanical waves due to Doppler effect are if the source is moving, the formula is f dash, that is the received frequency, is equal to the original frequency v over v plus minus u of the source. Okay, us is the velocity of the source, and moving observer if we are having, then it will be v plus minus u naught, where u naught is the velocity of the observer, v is the velocity of the wave. Done. F is the frequency, natural frequency of the wave. F dash will be the received frequency.
Yes, ma'am.
Understood?
Yes, ma'am.
Okay. So these are two different formulas. Okay. Now let me explain you this thorough topic in detail. Okay. But you got the crux of it? Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Now let's have a look. Check this diagram. So here you will see that if you ever stood, if suppose you are standing next to a busy road, then even many voices you might have noticed that the car sound becomes different when it comes towards and when it goes away. Okay, and it is also difficult to actually explain this, right? Like why it is happening and what is the effect. So the sound on the approach of higher frequency than the actual frequency is known as Doppler effect. Okay, so the changing frequency and amplitude of the wave with the moving source and the observer, okay, or I should say between the source and the observer, effect of that is known as Doppler effect. Any doubts?
No, ma'am.
Okay, so here let's start doing a study of this particular factor. So here this person, you can see a car is moving and it is coming towards person 1 and it is going away from person 2. Okay, so as soon it's moving, he will only observe the light wave which is going which is going away from him, and this particular person will check that the light is coming towards him. Okay, so now this particular topic comes under relativity, Akshita, that
Yes.
if from here the car had started, okay, let me give you this. From here, suppose the car had got started and it is traveling towards him, wave will get shorter. As I had told you, the frequency will become high. Okay, because it will shrink. The waves will become shrink, isn't it? Okay.
Yes.
So the distance it had traveled is obviously Vt.
Yes, ma'am.
And as it is coming towards, so this shrinkage will be shown as Ct minus Vt. Ct is what? The distance light is traveling. Which light? Headlight of the car.
Yes, ma'am.
Okay. So the
Yes.
total distance from the person to the car where it started is Ct. And it is decreasing the distance of Vt as it is coming towards the person. So every time he will receive Ct minus Vt voice. Understood or not? Or the light. Because in car we get the both.
Yes, ma'am.
Correct? Akshita, any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Similarly, you can compare it here also that from the starting position, the person is standing over here. Hence, it is covering how much distance? Ct. Okay?
Yes,
And
ma'am.
as it is going away, so you have to add in this Ct this distance also. Understood or not?
Yes, ma'am.
Okay. So, shall I start the mathematical part of this if you have understood the diagram?
Yes, ma'am.
Okay. Then start doing that also. Okay. So now check. Uh, Basically here what is happening? A car is started and from the red spot it got started, right? It
Yes,
had
ma'am.
started from the red spot and it drives forward with the speed of v and it is traveling for t seconds. Okay. So the speed of the car I'm talking about right now. Speed is v. Time it's taking is t. Okay.
Yes, ma'am.
And it is producing a sound of frequency, let's say f naught. Okay.
Yes, ma'am.
Okay. So in this time t, the source produces, I guess, in time t, the source produces f naught t complete waves. Correct?
Yes, ma'am.
Okay. So ahead of the car, these waves have been squashed, or I should say shrink up. Okay. In what distance? Ct minus Vt distance?
Yes, ma'am.
The squashed part that you are observing is this much. Correct?
Yes, ma'am.
Okay. So what should be the wavelength? Let's calculate the wavelength. So the wavelength will be Ct minus Vt over f naught t. Tell me your doubt. C equals to f lambda, Akshita. So what
Okay.
will be lambda? C over f. So C minus V is the distance traveled. Ct minus Vt. Correct or
Yes.
not?
Yes,
By the
ma'am.
light in
Yes.
f naught t. So from everywhere t will get cancelled out and you are remaining with this much. Any doubts?
No, ma'am.
Okay, good. So the velocity of these waves is c. Okay. So therefore, the observed frequency f1 will be how much? C over lambda 1.
Yes, ma'am.
So what will be the observed frequency if I put? It will be C over C minus V over F naught.
Yes, ma'am.
This will be V naught. Sorry, my bad. We are having this value from here. Check.
Okay.
Any doubts?
Means V by. Okay, ma'am.
Okay. So basically, I can rearrange it as CF naught over C minus V.
Yes, ma'am.
Any doubts?
No.
Okay. So this is F1. Now, if we do the similar derivation when the waves coming from the behind is observed, then it is traveling Ct plus Vt distance, okay, in time t. Correct?
Yes, ma'am.
So therefore, here my observed frequency will be Cf naught over C plus V. So therefore, the frequency is nothing but Cf naught over C plus minus V. Any doubts?
No, ma'am.
This will be the observed frequency. That means what we are hearing when it is coming towards and going away. Okay?
Okay, ma'am.
Okay. Now let's talk about moving observer. You want to write it?
Yes, ma'am. 1 second.
Yeah, sure. Otherwise, I have shared the page with you. I hope you have got it.
In my mail ID, ma'am. In
No, I had shared it with Miss Sonia and I had told her to share it with you.
okay, ma'am.
Yesterday itself, I had done that. Did you got it?
No, ma'am. 1 second.
Not
Oh,
yet?
I think there is another link down. Maybe if I press the
Just
OneDrive.
check it once.
Oh,
If you have got.
maybe if I enter my mail ID, it will come. I
Okay.
thought that was like a class link, ma'am. I didn't. Uh, 1 second. I'm just checking it now.
It's okay. I have shared it on her WhatsApp only number.
Yeah, yeah.
Regular number. Yeah.
So asking for next, and then it is not going like I'd asked for my mail ID. I gave my mail ID.
Okay.
Need you to enter the mail that this item was shared to Rekha.
It's okay. I will tell her again. Don't worry. It's okay.
Okay. I'm
Yeah.
not
Don't
able
worry.
to, but yeah, enter the next button.
It's okay. It's okay. It's okay. I will do again.
Okay.
Okay. Yeah.
Yes, ma'am.
Shall we move ahead now?
Yes, ma'am.
Okay. So here I had given you the example of moving observer. Okay.
Yes, ma'am.
Have you written that part?
1 second, ma'am. I was writing the formula of the observed frequency once. Yes,
Written?
yes,
Okay. So in moving observer, Akshita,
yes.
correct?
I can't hear you, ma'am.
Yeah, sure. Now is it audible?
Yes, ma'am.
Okay. So I am saying car 1 and car 2 is visible.
Yes, ma'am.
Okay. Can you
Again it went, ma'am. Like it is breaking and then coming. Hello, ma'am? Ma'am? Hello, ma'am? Hello, ma'am? Hello, ma'am? Can you hear me? Hello, ma'am? Ma'am, can you hear me, ma'am? Ma'am? Uh, hello, ma'am? Ma'am, can you hear me now?
Yeah, you are
Yeah.
audible. Now am I audible to you?
Yes, ma'am. Yes, ma'am. Now it is clear.
Clear, no?
Yes, ma'am.
Great. So what I was telling is, can you see this car?
Yes, ma'am.
Okay, so car 1 and car 2 is moving and now the source is at rest.
Yes, ma'am.
Okay, the source is at rest. Correct?
Yes, ma'am.
Okay. So now, here, if you see the relative velocity of the sound for the coming car, that is the car 1, obviously. Okay, let's
Yes.
check the relative velocity of car 1 that is coming towards. This is towards example. Done. So it will
Yes.
be nothing but C plus V, isn't it?
Yes. Yes, ma'am.
C from here is the source. So from the source the light is going and it is moving with velocity V. So the person who is sitting inside will receive it as C plus V, isn't it?
Yes, ma'am.
Okay. So now after this, the frequency which will be observed by him will be C plus V over lambda. Okay. Why did I say that? Because lambda equals to C over F naught.
Yes, ma'am.
This is what we had seen, right? So I
Yes, ma'am.
can again write it and rearrange it as C plus V F naught over C. Correct?
Yes, ma'am.
Check what I had written. If I'm going correct. I had placed this value over here.
Okay, ma'am. C
So I
by
got this value.
4 by 6. Yes, ma'am.
Observed frequency. Isn't it?
Yes, ma'am.
Okay. So now let's calculate when for car 2. So now light is traveling in this direction with C. Car is moving in this direction with V. So I think he will receive as C minus V. He will receive as C plus V.
Yes, ma'am.
Okay? Done. So therefore, I will be writing my F2 as C minus V F naught over C. Done. So the combo of this will be F equals to C plus minus V F naught over C. Okay?
Yes, ma'am.
Done. Now let's talk about a numerical over it. Okay, till that time you can write it.
Okay, ma'am.
Are you done?
Yes, ma'am.
Okay. So here is the question. Check. A car is traveling with 30 meter per second. Sound frequency is 500. Calculate the frequency of sound measured, that is observed by the observer. Okay. So the car is traveling and the person is at rest. So my formula would be C1 equal to CF naught over C minus V. Correct?
Yes, ma'am.
Okay. So here, basically, the source is moving, okay, with relative to the observer who is stationary with relative to the medium. And he is moving with respect to medium. Check as per the
Yes, ma'am.
question. Correct or not?
Yes, ma'am.
Did you got it or not? A car is traveling at 30 meter per second, emits a sound of frequency this much. Calculate the frequency of sound measured by the observer in front of the car.
Yes, ma'am.
So observer is standing in front of the car, so he is stationary. Whereas car is traveling, so source is moving because it is emitting the sound wave. Okay. So the
Yes, ma'am.
source is moving, observer is stationary. Now, did you got how did I put the answer?
Yes, ma'am.
Okay. So it will be what? Let's put the values. It will be 340 for sound wave, correct, in air. F naught will be 500, correct.
Yes, ma'am.
340 traveling is 30 meters, so it will be this. So F1 I got it as 548 hertz. So the observer will receive this much of frequency. Done?
Yes, ma'am.
Okay. Now let's move ahead. The Doppler effect and EM radiations. So till now what we have discussed was the sound wave in air. Now I am discussing your red shift, blue shift, green shift, like that. Okay.
Yes, ma'am.
Okay. So basically Doppler effect is also applied to the EM radiation. Okay, Akshita. Like your radio waves, microwaves, light wave, etc. Okay, and a formula is derived for it. Okay, and since the velocity of light never changes with relative to the movement of any observer, so the velocities are much smaller as compared to the speed of light.
Yes, ma'am.
I'm saying, listen to me again. I'm saying the derivation of the formula is rather more complicated. Okay, because the velocity of light never changes
Yes, ma'am.
with relative movement of the observer. Does it
Yes, ma'am.
change?
No, ma'am.
No. Yes. However, if we have the relative velocity is very smaller than the speed of light, then we use some formula. Okay. Let me give you that formula now.
Yes, ma'am.
So it moves with this formula. Okay. That is delta F. That is the change in frequency will be V over C. V is the speed of the source and observer. C is the speed of light. F naught will be the original frequency. Done?
Yes, ma'am.
Okay. So with the help of this, if you are having a very small velocity of any moving object with relative to the speed of light, you can use this formula. Done? Now,
Yes,
how
ma'am.
is it helpful? Let's have a look over that. So it is helpful in redshift and blue shift. Let me explain you what is that now. Okay. Check this picture.
Okay, ma'am.
This is redshift. Okay. Now let me explain you this part.